Welcome to today's paper reading. Today's paper is titled, Fine-Tuning Image-Conditional Diffusion Models is Easier Than You Think. This paper was published on vision.rwth-aachen.de by Gonzalo Martin Garcia and colleagues from RWTH Aachen University. The abstract highlights recent advancements in monocular depth estimation using large diffusion models. These models treat depth estimation as an image-conditional image generation task, achieving state-of-the-art results, but with high computational costs. The authors identify a flaw in the inference pipeline that, once corrected, significantly reduces computational demands while maintaining performance. They also introduce an end-to-end fine-tuning approach on a single-step model, which outperforms other diffusion-based models in depth and normal estimation tasks. Figure 1 illustrates the process of repurposing diffusion models for geometry estimation through end-to-end fine-tuning. On the left, the figure showcases the depth and normal predictions generated by our method on images captured in real-world settings. These predictions demonstrate the effectiveness of our approach in handling diverse and complex environments. On the right, the figure highlights a critical fix applied to the DDIM scheduler, which allows for single-step inference in recent diffusion-based depth estimators. This fix significantly enhances the speed and accuracy of the models, making them more efficient and practical for real-world applications. Additionally, the figure emphasizes that simple end-to-end fine-tuning can outperform more complex diffusion baselines, indicating that the perceived inefficiency of diffusion models for geometry estimation can be addressed through straightforward fine-tuning techniques. Monocular depth estimation is widely applied in various tasks including image and video editing, scene reconstruction, and robotic navigation. Recently, diffusion models have been adapted for this task, showing high levels of detail but are known for their slow inference speed. In this paper, the authors focus on achieving reasonable predictions with a single inference step by fixing a critical flaw in the inference pipeline of models like Marigold. This correction allows for performance comparable to multi-step inference while being significantly faster. In monocular depth estimation, the simplest form is relative depth, which ranks objects by depth without absolute measurements. Metric depth, on the other hand, requires modeling the focal length, introducing complexity. Affine invariant depth is a middle ground, preserving distance ratios without focal length dependency. For generalization, zero-shot methods like MIDAS and VIT-based models like DPT and Omnidata have been pivotal. In monocular normal estimation, predicting surface orientations has seen advancements with models like Omnidata and Metric 3DV2, which can predict both depth and normals. Figure 2 presents visualizations of Marigold's depth map predictions. Panel A shows the RGB input image used for depth estimation. Panel B displays the pixel-wise standard deviation heat map of Marigold's depth map output during a 50-step DDIM inference process. Panels C and D illustrate Marigold's depth map predictions before and after fixing the inference pipeline, respectively. This figure highlights the impact of the inference pipeline fix on the accuracy and efficiency of Marigold's depth map predictions. Latent diffusion models, LDMs, operate within the latent space of a variational autoencoder, V, which consists of an encoder and a decoder. The encoder compresses input data into lower-dimensional latent codes, while the decoder reconstructs the input. In conditional diffusion models, both the forward and reverse processes are conditioned on an additional input, such as a text description or an image. The network is trained to denoise the input based on this condition. Marigold, a model for depth estimation, utilizes a conditional latent diffusion process, building upon pre-trained models like Stable Diffusion. It is expected that Marigold's single-step prediction will yield a sensible, albeit blurry, depth map. Figure 3 illustrates the diffusion training process of Marigold for generating conditional depth maps. Marigold begins with a pre-trained Stable Diffusion V2 model, which is then fine-tuned specifically for the task of generating depth maps or surface normal maps based on image conditions. According to the argument presented in section 3.1, we anticipate that Marigold's single-step prediction will yield a sensible yet blurry depth map, reflecting the model's training and conditioning on image inputs. The diffusion-based depth estimation models, while performing well, exhibit artifacts such as blurred or oversharpened outputs. This is likely due to the diffusion training objective not aligning with the desired downstream task. To address this, the authors propose end-to-end fine-tuning of the diffusion model. This approach fixes the inference pipeline and ensures single-step predictions, making it computationally feasible. During training, the time step t is fixed to t, noise is replaced with the mean of the noise distribution, and only the RGB latent is forwarded through the model. Figure 4 illustrates the inference procedures of Marigold, top, and our proposed simplification, bottom. Marigold's method involves a diffusion process, whereas our proposed method is deterministic and operates using RGB latents without noise. Notably, the time step is fixed to t for the simplified model, which streamlines the process and enhances predictability. The experimental setup involves using specific datasets for training and evaluation. For training, the HyperSim dataset, which consists of photorealistic indoor scenes, and the Virtual Kitty 2 dataset, which covers driving scenarios, are used. Both of these datasets are fully synthetic and provide high-quality ground truth annotations. For evaluation, the models are tested on commonly used benchmarks for monocular depth estimation, including NYUV2 and ScanNet for indoor environments, ETH3D and Diode for both indoor and outdoor scenes, and Kitty for outdoor driving scenes. The evaluation is conducted in a zero-shot setting, using affine invariant depth predictions with the standard approach of scale and shift optimization between the predicted depth and the ground truth. Figure 5 illustrates the depth estimation results across various inference steps. Notably, the fixed inference strategy consistently surpasses the original Marigold method, particularly in single-step scenarios. The effect of ensembling, indicated by 10 ends, remains significant during multi-step inferences. Additionally, the deterministic end-to-end fine-tune baseline demonstrates superior performance over all other variants of Marigold. Figure 6 presents qualitative results from fixed single-step and ensembled multi-step Marigold models, as well as deterministic end-to-end fine-tuned models based on both Marigold and GeoWizard. Notably, the multi-step results exhibit noise-like artifacts, contrasting with the sharper and more accurate predictions of the end-to-end fine-tuned models. These findings underscore the effectiveness of fine-tuning in enhancing model performance and reducing artifacts. Further qualitative results are available in Appendix D for a more comprehensive understanding. Table 1 presents the main depth estimation results, highlighting that distilling Marigold with LCM yields inferior performance compared to applying a fix without retraining. The table shows that task-specific training significantly boosts the model's performance across various datasets. Additionally, it provides inference times for different methods, ranging from 121 milliseconds to 24 seconds on an NVIDIA RTX 4090 GPU at a resolution of 576 by 768 for a single image. The results underscore the importance of task-specific training and the impact of different inference steps on model performance. Table 2 presents the main results of normal estimation using Marigold, which has been trained and evaluated by the authors. The table compares various methods across different datasets, highlighting the mean angular error, mean, and the percentage of pixels with an angular error below 11.25 degrees. Key results include Marigold, 50, 10, achieving a mean angular error of 18.8 degrees, Marigold with DDM fix reducing this to 17.4 degrees, and SD with E2EFT further improving to 16.5 degrees. These results underscore the effectiveness of different strategies in enhancing normal estimation accuracy. Table 3 presents the results of applying a fixed DDM scheduler and end-to-end fine-tuning, E2EFT, to the GeoWizard method. The table shows significant improvements in both inference time and accuracy across various datasets. Specifically, the inference time for a single 576 x 768 pixel image is reduced to 254 milliseconds on an NVIDIA RTX 4090 GPU. The mean angular error, mean, on the NYUV2 dataset decreases from 17.0 to 16.1, and the percentage of pixels with an angular error below 11.25 degrees, 11.25, increases from 56.5 to 60.7. These improvements highlight the effectiveness of the applied techniques in enhancing GeoWizard's performance. Table 4 presents the impact of different types of noise on the task-specific fine-tuning for depth estimation. The table compares the effects of Gaussian, pyramid, and zeros noise on metrics such as absolute relative difference, ABS-REL, and delta-1, delta-1, across various datasets including NYUV2, KITTI, ETH3D, ScanNet, and Diode. The results indicate that Gaussian noise generally increases ABS-REL and decreases delta-1, while zeros noise consistently improves delta-1. Pyramid noise shows varied effects depending on the dataset, with some improvements in ABS-REL and delta-1, but also instances of increased ABS-REL. In comparing with Marigold, the fixed DDIM scheduler reveals that Marigold's multi-step denoising is not effective. Instead, it worsens performance due to error accumulation. However, ensembling still offers benefits with at least 2 inference steps. Regarding performance metrics, the study shows that Marigold LCM performs similarly to vanilla Marigold with 50 steps on outdoor data but slightly worse indoors. End-to-end fine-tuning significantly improves results, especially on NYUV2. In terms of state-of-the-art comparisons, the fine-tuned models outperform current generative methods for depth estimation on most datasets and set new records for surface normal estimation, except on NYUV2 where metric 3DV2 remains superior. Table 5 provides a comprehensive comparison of various state-of-the-art depth estimation methods across multiple datasets. Key findings include Midas, 39, achieving a delta-1 of 88.5 on NYUV2, Depth Anything V2, 52, scoring 4.4 ABS-REL on the same dataset, and Marigold plus E2 EFT reaching 5.2 ABS-REL on NYUV2. The table also highlights the performance of other methods such as LURI-S, 55, Omnidata V1, 12, and HDN, 56, among others. Notably, metric 3DV2, 23, was trained on ScanNet, making zero-shot evaluation on this dataset impossible. Results that were not reproducible with the released code and models are grayed out for transparency. Table 6 presents a comparison of state-of-the-art normal estimation methods across various datasets. Key methods include Omnidata V1, metric 3DV2, and GeoWizard, with notable metrics such as mean error and accuracy within 11.25 degrees. The table highlights the performance of each method on datasets like NYUV2, ScanNet, IBIMS-1, and Cintel, providing insights into their effectiveness and reproducibility. In this study, the authors identified a critical flaw in the implementation of the DDIM scheduler, which has led to potentially incorrect conclusions in several prior works. They found that simple end-to-end fine-tuning methods outperform more complex training pipelines and architectures. Despite this, their work supports the hypothesis that diffusion pre-training provides excellent priors for tasks such as monocular depth and normal estimation. The resulting models enable accurate single-step inference, benefiting from large-scale data and sophisticated self-training procedures. The authors believe that further improvements in diffusion models will lead to even more reliable priors, potentially enhancing the performance of geometry estimation models, making this a promising area for future research. The research conducted by Karim Abu Zaid is supported by the Bosch RWTH LHC project, specifically focusing on context understanding for autonomous systems. Additionally, Christian Schmidt's work is funded by the BMBF project Bridging AI. Computational efforts were facilitated by resources granted by RWTH Aachen University under the project RWTH 1690. Thank you for watching.